ICMP Essentials. In the world of IP routing, ICMP will prove to be one of your most useful troubleshooting tools. In this nugget, we will define ICMP. We will understand where ICMP fits in the big picture. Then we will examine the ping and the traceroute commands to see which ICMP message types are in use. We'll end up with a look at the redirect and the unreachable message types. Any good definition of ICMP is going to start by breaking out the acronym. ICMP stands for Internet Control Message Protocol. Its purpose? To provide informational messages concerning the routing of IP datagrams. As you can see here, messages, and we're going to control Internet or IP routing of datagrams. It's going to do this in two ways. There's two types of informational messages. The first is a query and response pair. The most popular is probably ping, and it's used to send out a query to a destination, and if that destination responds, we know that it is up and alive. The other type of informational message is an error message, simply stating, hey, within the path that you chose to get from point A to point B, there was an error, and this is what happened. ICMP is part of the TCP/IP protocol. So in that sense, I have a model here of the TCP/IP stack, the application layer, the transport layer, the network, and the link. I've also shown you here the OSI model and how they map together. But ICMP resides at the network layer, which really makes sense, right? Its job is to monitor and control network traffic. And what better place to do that in than at layer 3 so they can see any of the errors that might come into play. Now, even though it's at the same layer as IP, the network layer, all ICMP messages still ride in IP packets. In other words, it has an IP header, which is up here for your reference if you need it. Following that, we have specific fields for the ICMP messages. The first field, a type. The second is a code, and the third is a checksum. The type field is going to give you the type of message that we're dealing with. The code is going to give you more granularity in a specific type of message. There are many message types available in ICMP. I've listed them here. Keep in mind, though, that this is beyond the scope of the CCNA objectives. I simply include it for informational purposes in your reference as you pursue your career. We do see, as I said, the types here. 0, 3, 4, 5. Note they're not sequential, but they do run from 0 to 18. I have the descriptions here. And then here, the two categories, as I'd mentioned before. Either it is a query response pair or it is an error. So when I say query response pair, you can imagine like the echo request and the echo reply work together. And then the timestamp request and the timestamp reply work together as well. Note here that I only have 5 messages that are error type messages. And the interesting point about the error messages is that they are the only ones that have more than one code available to them. As with the message type list, I include this simply for your reference. We have a type 3 message here, which is an unreachable message, and every code available underneath. As I had said before, it offers a bit more granularity into that type of message, whether it was a network unreachable, a host unreachable, protocol, or port. So far, we've defined ICMP, and we've learned in a big picture sense where ICMP resides. Next, we get into the meat. We're going to look and examine the ping command to see exactly how the echo request and echo reply message types are used. Let's start by looking at the purpose of a ping. It's to verify connectivity between 2 IP points on a network. 2 IP points is critical, and network too. Understand, I'm not limiting myself to a local area network. These 2 computers can be side by side, or they can be across the world as long as both of them have connectivity to the same network. In most cases, that will be the internet. Let me get you familiar with our diagram here for our points of discussion. I have a computer N1 that's connected to a hub. Off of that hub, I have a firewall, and I have the internet hanging off of the firewall. I also have a router, R1. R1 has connectivity to another network, and on the other side of that network is R2. The 2 networks we're talking about, 192.168.1.0 with a 24-bit mask here locally, 192.168.2.0 with a 24-bit mask here locally. All right, let me give you my 2 examples. In the first example, I'm going to have N1 trying to ping R1. Here we see N1, and here's R1. The first thing that happens, N1 sends out an echo request. As soon as R1 receives that, understands that the destination is his IP address on this interface, he will submit an echo reply back to N1. At that point, we verified two things. One, that there is connectivity between N1 and R1 on both directions, and that R1 is alive. In my second example, I'm going to ping from N1, but this time to R2. So from N1 to R2. Here we go. The first thing that happens is N1 sends out an echo request. It traverses R1. He forwards it over to R2. R2 receives the packet, understands that it's destined for this IP address on this interface, and then responds with an echo reply back to N1. So far, it looks like exactly the same thing as our first example. So why did I include it? The reason is I wanted to illustrate that no matter how many routers this request and the reply traverse, it will look exactly the same on both endpoints. At this point, we're going to run both of these examples through our lab. Things to remember within our configuration up here. N1 has a gateway of 192.168.1.2. Not .1 here, but .2. All right, router 1, which is this network, has directly connected routes to 192.168.1 and 192.168.2. And last, N1 captures data with a sniffer. All right, let's make this happen. I'm in a Windows environment, and I'm going to pull up a command box. The command I'm going to issue is ping 192.168.1.2. Remember, I am at N1, and I am pinging R1, this interface here. All right, here's our results. What we're seeing in the results is we did indeed get a reply from 192.168.1.2. This is the number of bytes associated with that packet. The time for the round trip was less than 10 milliseconds, and it had a time to live of 255. Now let's take a look at our trace. What we see here is Nugget as a source, 192.168.1.2 as a destination. It is an icmp packet. First we have our echo request, as we had indicated earlier in our diagrams, and then right after that we have 192.168.1.2 as a source now. Nugget 1 is the destination, and it's an icmp message, and this time it's the reply. And we see that repeat 4 times. Isn't this output amazing? I'm telling you, a sniffer will accelerate your learning immensely whenever you use it in your lab and you're modeling protocols from one PC to another. Now we'll run our second scenario. Here I have a ping for 192.168.2.2, which is again sourced at N1, routing to the interface on R2. Let's see what happens. As before, we have success. I see replies coming from the destination that we had chosen. Again, 32 bytes, round trip time was less than 10 milliseconds, and time to live was 254. Why is this the only difference? We're going to learn about that. From N1 to N2, I traversed a router. Every time a packet traverses a router, it takes the time to live that it receives, decrements it by 1, and then sends the packet on. So by the time it came to R2, you have a time to live of 254 rather than 255. Let's take a look at our trace. Here we have it. The first packet from Nugget 1, destination 192.168.2.2, icmp protocol, it's a ping request, just as like we saw before. Now the response. From 192.168.2.2 to Nugget 1, icmp protocol, here's the reply. So just as we said in the diagram, as far as icmp is concerned, there is no difference whether you traverse a router or not between the request and the reply. Understand we did draw one distinction. In the IP protocol here, we're going to decrement the time to live 1 every time that we hit a router. That concludes our discussion on the simple ping. Next we're going to look at the trace route. As usual, we'll start our discussion out with the purpose. The purpose of traceroute is to track the hops, network layer devices, between 2 points on a network. Now by network layer devices, we're really talking about layer 3. All right, there are a couple of key rules that allow traceroute to be successful. Let's look at those. The first is the TTL, which is short for time to live, is incremented by 1 in each packet group. What do we mean by packet groups? All right, when we send out a traceroute from N1 that is destined for N2, the first thing we do is it sends out 3 consecutive echo requests. Each of these echo requests has a time to live of 1. The next packet group that's sent out, we see here, is another group of 3 echo requests. The difference in this group is going to be that its time to live is 2. And then we have a third set. 3 of these will be sent out with a time to live of 3. Let's look at our second rule to find out why this is important. Every router decrements the TTL, or time to live, by the processing time in seconds. All right, when this packet gets to R1, it had a time to live of 1. R1 will take some computing time on that packet. It is never as long as a second. But this measurement is in seconds, so the least I can take away is 1 second. When I decrement this by 1, I'm going to have a time to live of 0 on a packet residing at the router. Let's look at our next rule. If a router receives a packet with a TTL of 1, it must send a time-exceeded error message back to the originating source. All right, so we received a packet with a TTL of 1. We processed that packet, decremented it down to a time to live of 0, and now our requirement is to send back an error message. And this specific error message is an icmp time exceeded message to N1. As we said earlier, the next group of packets to go out is going to have a time to live of 2 this time. So what happens at R1? One of these packets will arrive at R1. It is going to obey this rule and decrement the time to live by 1. So when it leaves R1, it's going to have a time to live of 1. That packet will still go on to R2. When it hits R2, now is when it has to obey the third rule of the router receiving a packet with a TTL of 1, and it sends back a time exceeded message to N1. Now the third group, we now send out icmp echo request with a time to live of 3. When it gets to R1, it'll decrement by 1, a time to live of 2. When it gets to R2, it'll decrement by 1 and have a time to live of 1. So when it arrives at N2, it'll have a time to live of 1. Now will this computer act as a router does? It won't. And let me tell you why. Because this is our destination. When N1 has been sending out these echo requests, the IP address as a destination was the interface here on N2. This echo request finally arrived at that interface. So, just like we saw in the ping command before, an echo request will result in an echo reply back to the originator. So this looks pretty familiar, right? This is the ping transaction we saw earlier. All right, now we're ready to see this live. As before, I'm going to pull up a command prompt. I'm going to type in traceRT. Because this is a Microsoft environment, that's the command for traceroute. The address we're going to traceroute to is 192.168.2.2. Now in our diagram, remember I'm at N1. We're tracing to this address. You got to ask, why not N2? For the purposes of our discussion, I went from N1 to N2 so that I could drive home the point of what happens on a time to live and how it's decremented at every router. But for the purpose of our live demonstration, I'm going to keep it just to 2.2 because I don't want the trace to get too long and we get caught up in too many packets and lose the point of our lab. And we're off. What we're going to have going on behind the scenes, N1 is going to send 3 echo requests to R1. R1 is going to respond with a time exceeded message back to N1. And we're going to see that in this first line. The next thing that happens is N1 sends echo request to R2, which is the destination of our traffic. Because of that, it's going to skip down to this last line and send back echo replies to N1. And we see that in this last line. Let's review this on our trace. All right, first packet to go out from Nugget 1, destined for 192.168.2.2. It's never going to get there though, and the reason for that is, we see it down here in the details. It is a type 8, so it's an echo request. But inside the Internet Protocol, we see a time to live of 1. Because of that, it's going to get to that first router. The router is going to obey the rule of anytime it receives a packet with a time to live of 1, it sends back a time to live exceeded message. And you'll see that here. This isn't from the destination. This is from the router in between, 192.168.1.2. Because this address is included, that's why in the traceroute command, you will see the response time for the 3 packets, and then the router that sent it back. So this is going to happen 3 times. Request, time to live exceeded. Request, time to live exceeded, and then for the 3rd time here. This 4th packet is going to go from Nugget 1. The destination is 192.168.2.2. Will it make it this time? It will, because you look here. Time to live is now 2. And that's enough to get to our destination. And because it is, we get an echo reply back, and we get a series of 3 of them. I love the output of this sniffer. You got to realize that without sniffers and their technology and the trace that we can review after we've performed a test, we wouldn't see this detailed information. It's kind of like the Toy Story, for those of you that have seen it, when Woody's standing in front of all the toys and he says, he's talking about moving buddies, if you don't have one, get one. Same thing with sniffers. If you're going to be in this profession, get one. The particular sniffer we're using here is Ethereal. It's not free. You can get it on the web, but it really is worth it. It's a great tool. All right, so far we've defined ICMP. We looked at the placement in a big picture sense of ICMP as well. Then we looked at the ping and the traceroute commands and found out exactly what message types of ICMP they use. Next, we're going to look in detail at the redirect message. Redirect messages can be a common occurrence on a local area network. In fact, they're not always due to misconfiguration. Sometimes you can use a redirect to point a number of hosts within your local area network to a temporary gateway to the internet without having to go to each computer and reset the gateway. As you can easily guess, the purpose of a redirect message is to redirect misrouted packets to the best path. Simple enough, right? Let's take a look at the packet. First, we're going to have the type field. This is a type 5 for redirect. Then the code field. This is where we get more granular with the type of redirect. There's 4 options here. We're going to discuss the first 2. Then a checksum, and then the most important field in the packet, the corrected gateway. This is where the redirect router will tell the host this is actually the IP address that you should be sending this packet to. After that, we have the original IP header plus the first 8 bytes. Before I show you exactly how a redirect works, let me get you familiar with our diagram. Again, we have N1. It's on the network 192.168.1.0 with a 24-bit mask. Its IP address is 254. We have router 1, who has an interface on that same network, and .2. We have a firewall with an interface on that same network as .1. Now, on the other side of the firewall is where we have the internet connectivity and eventually N2. The destination of our packet is going to be from N1 to N2. The problem is going to lie in the fact that N1 has a gateway of 192.168.1.2, which is router 1. Its gateway is not .1 as it should be to point out to the internet. And in some cases, that may be by design. If you'll remember, sometimes it will save us some rework if we use the redirect to our advantage. So let's say that N1 is a client of a server that hangs off the router, R1, on another network. Most of the traffic runs from N1 to this server and back. In this case, using the gateway of this interface on R1 is actually the best thing to do. Very few times will I have traffic running to the internet. In the times that it does, we will rely on a redirect message to get it there. Let's examine the mechanics of a redirect now. The first packet is going to go from N1 as a source, and the destination is N2 listed in the packet. Now, because N2 doesn't reside on the local area network, that is in 192.168.1.0 with a 24-bit mask, N1 has to send it to its gateway, which in this case, as we discussed earlier, has been set to this interface on R1, and it trusts that R1 will get the packet where it needs to go. All right, R1 receives this packet. First thing it's going to do is look at its route table. And in this route table, it has specific routes for this network on this side and a network on this side. After that, it has a gateway of last resort of 192.168.1.1, which is the firewall. All right, because of that, it's going to say, you know what? I don't have a specific route to the network that I'm trying to get to, in other words, N2, and I have a gateway of last resort of firewall 1. That's on the same local area network as N1. So what I need to do is, first of all, do N1 a favor and send this packet to the firewall. The next thing I need to do is send a redirect message to N1 saying, I'm not the right person to forward this message to, and it provides that in that message, remember this field here, the corrected gateway, the address of the firewall, which is 192.168.1.1. Now, once N1 receives this redirect message, it's going to update its routing table, and it's going to say in the routing table, if I want to get to N2, specifically this IP address, I need to forward traffic to 192.168.1.1. All right, so the next packet that comes out of N1 destined for N2 is going to go through the firewall over to N2. And every subsequent packet thereafter in this conversation will run through F1 over to N2. All right, are you ready to go live with this demonstration? Let me bring up a command prompt. This is what we're going to do on this one. I'm going to ping www.nuggetlab.com. Now, I could have written that out in our demonstration here instead of N2, www.nuggetlab.com, but honestly I saved myself a little bit of writing, and this is actually where we're going to go for our destination out on the internet. So let's do this. Alright, the first thing you see here is that in our ping we had to resolve the name to an IP address. So we know we had a DNS resolver involved here. Once that IP address was pulled up, we started pinging that address directly. 32 bytes, 63 milliseconds, and then time to live was decremented as we talked about earlier. Let's take a look at the trace that we collected so that we can see the magic that went on behind the scenes. Alright, here we have it. The first thing we're going to see is Nugget 1 with a destination of cbtnuggets.com. Alright, now remember, in my ping, I was pinging www.nuggetlab.com. This is a completely different server. This is my DNS resolver. So I'm going to him with a DNS query, and it's just a standard query that says www.nuggetlab.com, what's the IP address? The first thing I get back is a redirect, but before I go there, let's understand why. If I look at the Ethernet section of this packet down here in the details, you see that Nugget 1 was the source, and the destination was this MAC address. And it tells you here that it's a Cisco MAC address. This is the only indication I have within this packet that tells me that I sent this to 192.168.1.2, which was set as my gateway, and it actually should have been sent to .1. This is where I see that. In the IP protocol, I see that this is a packet from my IP address at N1, destined for cbtnuggets.com, which is 63.241.181.46. The next packet I see is a redirect message. It comes to me from the Cisco router, which is R1, and it's 192.168.1.2, coming to Nugget 1. And what is it telling me? Let's look in the icmp portion to find out. Here's the icmp portion, Internet Control Message Protocol. It says, here's a redirect message, and here's the gateway address that you should actually be sending these packets to, 192.168.1.1. So now it's pointing me to the firewall. Next packet we see, alright, what is this? Remember I said the Cisco router does two things simultaneously. One is going to redirect me to where I should be sending this traffic, and then it's going to do me a favor by sending the original packet that I sent to the right destination. So, source, the Cisco router, which is R1, through the firewall, and I'm still asking the same thing. I'm going to my DNS server with a query. You see the DNS here. Alright, then I get the response back, and this is going to let me know what www.nuggetlab.com resolves to as far as an IP address. Now that I know the IP address for this name, I'm going to send a packet to it, and it's the icmp packet that I've been trying to send, and it's an echo request. So let's take a look at that. In the Internet Protocol section of the details, I see here Nugget 1, this is my IP address as a source, and the destination address is www.nuggetlab.com, but now I have its IP, 63.241.181.108. Alright, and besides that, it's just the standard echo request. What's the first thing I get back? A redirect. So you got to ask here, why do I get a redirect back if I've already been redirected here by the router at 192.168.1.2 telling me to go to 1.1? Alright, the answer is this. In this case, my destination on this packet was 63.241.181.46, or easier by the name cbtnuggets.com. So when I updated my routing table on Nugget 1, as I said I would, that update says if I'm trying to get to cbtnuggets.com, I go out 192.168.1.1. It doesn't say anything about getting to www.nuggetlab.com, which as we see here is a different IP address. In the fourth octet, instead of 46, it is now 108. Alright, so that's why I get another redirect, because I send this over to, as we see in the Ethernet section, I send it to the Cisco router again from Nugget 1. Promptly, I get a redirect back from the router to Nugget 1, and again as before, it's going to say, here's a redirect, the gateway address you actually need to use is 192.168.1.1. Following that, I get a reply back from my original request, and I make another request. Did I learn my lesson? I sure did. Now this request is going from source of nugget 1 over to my firewall. You see this is a different MAC address now. It's still in the IP section, this IP address for the destination of www.nuggetlab.com as a standard echo request. So let's look above here and see what happens next. I get my reply. I send another request, I get a reply, and then it happens again. And then that's all I see as far as my ping. But there's one more thing to take note of. The two redirect messages aren't the same. Let's look at the first one in detail. All right, it's an ICMP redirect. Let's look at the details section of ICMP. Here we go. Type 5, as you would expect. Here's the difference. Code 1. This is a redirect for a host. In the second redirect message, what do I see? I have a type 5 as well, but this time the code is 0. This is a redirect for a network. Let's discuss the differences. All right, network versus host redirects. As we saw in the trace, they have the same purpose. Essentially, they're the same type of packet, and they have the same effect. The difference comes in the code field. They're both type 5, but in the host, it's one number, and in the network, it's another. It's 0 or it's a 1, depending on which type. Where does the difference come in? The difference is in the route table. Okay, so we have our diagram here. The only thing I've included this time is a DNS server. When I say it's a difference in the route table, I am talking about the route table right here in R1. This is where that first packet goes for delivery out to the internet. Now R1 is going to look at its route table. If it has a route and it's a network route to the network you're trying to go to, you get a network redirect. If it's a specific host route, in other words, all 4 octets are specific in that route, then you get a host redirect. What better way to understand this than to go directly to the source? So let's go into R1 and look at its route table firsthand. Let me log in first. Enable, get into the privilege mode. Then we're going to use the show IP route command, and we'll see our routes. What we see here is a static route to 63.241.181.46. That's the cbtnuggets.com. That's the DNS server I had. That's why the first redirect was a host redirect. I had a route in here that was specific to that host. All 4 octets were specific, and I told it to go to 192.168.1.1. Now remember, with www.nuggetlab.com, it was the same 3 octets at first, 63.241.181. The fourth one, though, was 108. I don't have anything in here that specifically points me to 108. So I don't get a host redirect. The closest thing I have is this gateway of last resort that says, any network that you can't find, go to 192.168.1.1. This is why it resulted in a network redirect. That's fairly cool, isn't it? All right. That wraps up our conversation on the redirects. We saw a host redirect and a network redirect. Next, we're going to move into the unreachable type messages. In this section, we're going to talk about 2 types of unreachable messages. The first is going to be the host unreachable. Let's start with the purpose, to advise the packet source that the requested host is unreachable. So in the case of our discussion earlier, the packet source is going to be N1. And we're going to tell them that the host they're trying to get to is unreachable. All right, let's look at the packet. Type 4, this is simply saying it's an unreachable message. This is where we find the distinction between host and network. The code for a host unreachable is 1, for a network would be 0. Then you have the rest of the packet, including the checksum. All right, let's look at our diagram. N1 is directly connected to network 192.168.1.0 with a 24-bit mask. It has an IP address of .254. Router 1 has an interface on that same network with an IP address of .2 in the 4th octet. On the other side of router 1 exists another network, 192.168.2.0 with a 24-bit mask. Router 1 has an interface of .1. Router 2 has an interface of .2 on that same network. To start things off, N1 is going to transmit a packet to 192.168.2.3. Let's say it's a ping. All right, so looking at our network here, we see that the network 192.168.2 exists here. There is no .3, however, is there? So this is what's going to happen. N1's going to send that packet. R1's going to receive it. When R1 receives the packet, it's going to ARP out of this interface for .3. Now the problem is going to be that it doesn't exist. An ARP is simply a broadcast packet that goes out and says, I have an IP address of 192.168.2.3. Whoever has that address, please send me your MAC address so we can communicate. Alright, so after that times out and there's no response, R1 is going to transmit a host unreachable error back to N1. So you're going to see that error right here. And it's going to be this exact packet. In our examination of a network unreachable message, we're going to find very few differences, but enough that we see why we have a different result. First of all, the purpose is about the same. Advise the packet source that the requested network in this case is unreachable. We're going to have the same type, which says it's an unreachable type message. Now the code is going to be different. As we said before, a 0 code indicates that the network is unreachable. The rest of the packet being the same. Let's work out our diagram. N1 still, same network, 192.168.1.0 here, 192.168.2.0 here. This time, we're going to have a ping going from N1 with the destination of 192.168.3.1. Alright, so the network portion of this is here, 192.168.3. When that packet gets to R1, it's going to look in its route table. It's going to say, I know about this network, and I know about this network. I know nothing of .3. As soon as it knows that it has nothing in this route table for that network, it's going to return a network unreachable packet to N1, and it's going to look just like this. In this nugget, we defined icmp. We understood where icmp fits in the big picture sense. We also examined the ping and the traceroute commands. Then we ended up with a look at the redirect and unreachable message types. I hope this has been informative for you, and I'd like to thank you for viewing.